worker working as a assistant professor in KVN Naik College, Nasik. Today I would like to talk on stereochemistry of 1,2-disubstituted cyclohexane. Stereochemistry of 1,2-disubstituted cyclohexane. To start with, we all are quite aware that cyclohexane exists in a chair conformation because chair conformation is the most stable conformation. So, let us start with the cis isomer. Cis 1,2-disubstituted cyclohexane, and let us take both the substituents as CH3 groups. So, if you label this cyclohexane 1, 2, 3, 4, 5 and 6, these are the carbons. So, carbon number 1, if has CH3 at the axial position, then the methyl group of carbon number 2 has to be in the equatorial position. So, this is your first compound. Let us flip this compound and you get a second compound. And where the axial CH3 group goes to an equatorial one, whereas equatorial one goes to an axial position. This is your compound number 2. Let us take the mirror image of compound number 1. This becomes the mirror image of compound number 1. You get compound number 3, and mirror image of compound number 2. This is your compound number 4. If you see keenly, compound number 3 on flipping will give you compound number 4. So, compound number 3 and 4 are said to be conformational isomer as compound number 1 and 2. Compound number 1 and 3, these two are mirror images but non-superimposable mirror images of each other. So, these two are called as enantiomers. Likewise, compound number 2 and 4 is also called as enantiomers. Compound number 1 and 4 or compound number 2 and 3 are related as diastereomers. Now, let us check the energy associated with this molecule. Now, cis, there are two conformations available for cis isomer. One is AA and the other is EA. AE, EEA. Let us take the amount of energy associated with this conformer. So, the CH3 group is in the axial position. So, 1, 2 and 3. The third axial hydrogen will have 1,3 diaxial interaction. Likewise, 1, 2 and 3, this axial hydrogen also has an interaction with the CH3 group. Therefore, one axial CH3 group will give 2 1,3 diaxial interaction, and each CH3 edge interaction contributes to 0.9 kilocalories. So, total 1.8 kilocalories per mole of energy is associated for one axial substituent. The CH3 group at carbon number 1 and carbon number 2 equatorial position, these two are gauge to each other, and therefore there is one CH3 gauge interaction. There is one CH3 gauge interaction which contributes to 0.9 kilocalories per mole. Therefore, total amount of energy associated with this is 2.7 kilocalories per mole. Now, if you see compound number 1 and 2, they both are identical. There is one axial and another equatorial. So, both the isomers, conformational isomers, will possess 2.7 kilocalories per mole of energy. Now, let us go for a trans isomer. Now, in case of trans isomer, let us start with the equatorial one, CH3. If this CH3 is at the equatorial position in carbon number 1, then CH3 has to be in the equatorial position for carbon number 2. That is, one CH3 lies below the plane, the another CH3 lies above the plane, and this becomes your trans isomer. So this is your di-equatorial. So trans isomer, first possibility is di-equatorial. If we flip this conformer, flip it, the equatorial CH3 group goes to axial, so you have an axial. Likewise, carbon number 2 equatorial CH3 goes to axial position. So another isomer possible is diaxial, AA. Either you have EE or AA. Let us take the mirror images of these two compounds. Compound number 1, compound number 2. So these are the two CH3 groups, and if you go for this, these are the mirror images. If you see compound number 3, on flipping will give you compound number 4. So 3 and 4 are again 3 and 4 are conformational isomers, as 1 and 2 are conformational isomers. Now let us check the amount of energy associated with this molecule. So in this case, these two are gauge to each other. So therefore amount of energy associated is 0.9 kilocalories per mole, as there is only one gauge interaction. In case of diaxial position, each axial one will have 2, 1, 3 diaxial interactions. Right? 1, 2 and 3. So here you have 1, 2 and 3. Here you have. So here you have 1, 3, 1, 3. So in all there are 4 1, 3's diaxial interaction, that is with respect to CH3H. 4, 1, 3. So here 0.9 into 4, that corresponds to 3.6 kilocalories per mole. So amount of energy associated for trans AA will be 3.6. Now let us see regarding optical activity. Optical activities, this particular molecule does not have plane of symmetry. So obviously this it should have optical activity, but this molecule is not optically active because both are identical, both exist in the equal amount, and therefore they are optically inactive in spite of not having any plane of symmetry. Now let us go for relative stability order. Relative stability order of conformers. Okay. Now if you see, the most stable compound in this three is 0.9 kilocalories, that is for EE. So the most stable isomer is trans EE, contributing to 0.9 kilocalories per mole, followed by cis isomer cis AE or cis EA, which has got 2.7 kilocalories per mole, and the least stable is your trans AA, which has 3.6 kilocalories per. So stability wise, trans EE is the most stable compound and trans AA is the most unstable conformational isomer. With this, we end up with 1,2-disubstituted cyclohexane stereochemistry. Thank you.